A warm good evening to one and all co-present here. On behalf of PSNA College of Engineering and Technology and Department of Electronics and Communication Engineering, we welcome you all for the Day 3, Session 5 of the ATAL sponsored 6-day online faculty development program on Artificial Intelligence Techniques in VLSI Design. Now, I kindly request Dr. M. Triveni ma'am, Associate Professor of ECE, to give the introduction about the speaker. I welcome you, ma'am.
Thank you, sir. Welcome, Kripanidhi, sir. Welcome all the participants. Hope you have enjoyed the session for the past 2 days. So today, hope you all know Kripanidhi sir, who handled session 1. He's going to handle session 5 too. So a brief introduction about sir. Kripanidhi sir is an engineer in object automation with a background in electrical and electronics engineering from St. Joseph Institute of Technology, Chennai. He is working on open source projects with Microwatt using Vivado and OpenRoad, blending his skills in software and hardware for innovative automation solutions. He is skilled in various programming languages like Python, machine learning, full stack, and acquired various skills that are currently in demand. He used to provide training for college students, IT enthusiasts, and working people and help them enrich their knowledge in all the aspects. Hope this session will be useful for you. Sir, the session is yours. Please share your knowledge with us. Thank you, sir.
Oh, thank you. Good evening, everyone. Today we are going to see about the artificial intelligence and machine learning for the physical design automation.
Kausalya, ma'am, now
First,
only
what
speaking,
is
ma'am.
hello?
Sir, 1 second, sir. Introduction slide, sir.
Kausalya, ma'am. Is it audible now, ma'am? Okay, ma'am.
Okay, sir, you can start, sir.
Yeah. What is physical design automation? Physical design automation refers to the process of automating the steps required to convert the circuit design written in RTL, that is register transfer level, into a physical layout format called a GDS2. The RTL design describes the logics and behavior of the circuit, while the GDS2 is the final layout used for manufacturing the semiconductors. The PDA ensures this conversion process is efficient, accurate, and optimist. To achieve this PDA automation, there are several stages. That is for planning, placement, routing, and timing optimization. It's a in the first stage is physical design, where the chip's physical area is divided into blocks and major functional units are assigned locations. Factors like power distributions, heat dissipations, and interconnect lengths are carefully considered to create an efficient floor plan. In the placement step, individual logic gates, standard cells, and macros are placed within the predefined blocks. The placement process focus on minimizing the wire length and avoiding the condition while ensuring an optimal signal flow between the components. In the routing, after the placement, the components need to connect with the wires, often spanning multiple metal layers on the chips. Routing ensures these connections are efficient, free from the interface, and complies with the design rules. Yeah, next is timing optimization. This crucial case it ensures that all signal paths meets the timing constraints, meaning a signal reach their destinations with required time frames. It avoids potential issues like setups or hold time violations, which could lead to function failures. Uh, uh, PDA plays a pivotal role in the semiconductor industry, especially chip design becomes more complex with billions of transistors packed into a smaller areas. Here is why the PDA is essential in very large scale integrations. It ensures ensuring the power, performance, and area. Modern chip must be highly energy efficient, low power, and operate at a high speed and occupy the minimal physical area. PDA enables tools to make trades-off and optimization to meet this goal simultaneously and reducing the manual interventions. Without PDA, engineers would have to manually place components, route wires, and analyze timings, a process that is time-consuming and error-prone. Automation minimize the human involvement, allowing engineers to focus on higher level design considerations. This pressure shortening the design cycle time. The pressure to deliver the chips faster is immense in today's competitive market. PDA accelerates the design process by automating the repetitive and complex tasks, ensuring faster to market without compromising the quality. Uh, we'll see about the evolution of the power design automation. Physical design automation relied heavily on heuristics and algorithmic techniques to optimize various stages of chip design process. This method are role-based designs to address specific problems like placement, routing, timing analysis. Heuristic techniques used to practically problem-solving rules to find solutions that were good enough rather than optimal. Example, simulated annealing for placement optimization, where the algorithm iteratively adjusts placement to minimize the wire length or congestion. While this method provide a feasible solution, they often require a significant computational resource and manual adjustment for refinement. Algorithm techniques were developed to address the particular task like routing or timing. Example, static time analysis. Example, a search algorithm used to for finding the best route during the routing. Uh, we'll shift towards the AI and ML in power distribution. Uh, in With the increasing complexity of chip design, the industry turns to artificial intelligence and machine learning to address the limitation of traditional approach. Unlike the rule-based AL and ML, use data and learning-based models to adapt and optimize dynamically. The need for data-driven insights. Modern chips designs generates a massive amount of data at every stage of the design process. AI and ML can analyze this data to extract value insights. Example, prediction model. ML can analyze placement data to predict areas likely to experiment routing conditions and suggest preventive measures. Earlier identification of design reduces iteration and it will improve the efficiency. Faster convergence in design optimization. AI and ML significantly reduces the time required to explore and optimize the design solutions. Reinforcement dynamically adjust the placement or routing strategies by learning from real-time feedback during the design process. Train models on historic designs to predict the optimal parameters for placement and routing. Example, Google AI for you for TPU floor planning used RL to find floor plan 20 percentage more efficient than human generated designs within an hour. The the role of AI in power distribution optimization. Artificial intelligence is transforming the physical design automation process by introducing an advanced method that significantly enhance efficiency, accuracy, and adaptability. AI leverages predictive models, automated learning systems, and real-time decision-making capabilities to overcome the challenges faced by traditional methods. Predictive analysis. AI enable a predictive analysis by analyzing vast amount of design data to anticipate potential problems before they arise. This capability is crucial for early stage decision making makes in PDA. Early predictions of design flaws, AI algorithms can identify areas to issues such as congestion, timing violation, or power output early in design process. By doing so, engineer can address these flaws, reduce the need of cost rework during later stages. Predicting routing congestion after placement and adjusting flow plans to avoid uh, assisting the PPA estimation, that is power, performance, and area. These are the key metrics in chip designs. AI model analyze historic designs and simulate the future scenarios to estimate the PPA metrics, guiding optimization efforts. This early estimation helps ensure the design stays on track to meet its goal without unnecessary iteration. The benefit is that it accelerates the design process by catching the potential issue early and reducing the risk of missing critical deadlines due to several stages. Automation and learning. AI is replacing the traditional rule-based optimization method with the intelligent system continuously learns and adapts from rules to learning-based approach. Rule-based rely on predefined guidelines which may not be flexible enough to handle the complex or novel scenarios. AI, particularly machine learning, uses historic data to identify patterns and optimize the design process dynamically. Learning-based system can adjust placement strategies automatically based on previous design to improve the timing and reduce the violation. Unlike the static rule-based, AI can improve with more data and iteration. As more designs are processed, AI model becomes increasingly accurate in predicting outcomes and suggesting optimization. Uh, Estimating manual interventions, tasks such as parameters, cleaning, placement adjustments, and routing optimization can now be automated using AI, freeing engineers to focus on high-level design challenges. Real-time decision making. AI ability to analyze the data and make decisions in real time significantly accelerate the design iteration process in PDA, faster iteration placement and routing iteration. AI algorithms analyze the real time data during placement and routing to suggest adjustment uh, instantly. Example, an AI system can predict the congestion during the routing and reroute the path dynamically to avoid the delays. Timing closure optimization. Timing closure, one of the most time-consuming stages in ADA, benefits greatly from AI decision-making capabilities. AI identify critical paths and make adjustment to placement and clock tree synthesis to meet the timing constraint more efficiently. It will reduce the overall runtime of the design process and ensures a high success rate in achieving the design goals in fewer iterations. Machine learning in physical design. Machine learning has become a key play in the physical design by addressing a complex challenges that traditional methods struggles. AI techniques like predictive modeling, optimization, and automation are transforming critical stages of physical design, result in faster design cycles. The first, automated placement and routing optimization. Placement and routings are crucial steps in physical design where components are positioned and interconnected. ML enhance this by automating and optimizing them for better performance and minimal congestion. How the ML helps in placement optimization is The MI model analyzes the design data and predicts the optimal location for components, reducing the violence and improving the performance. Example, reinforcement learning dynamically adjusts the placement strategies to balance the area and timing constraint. Routing optimization, the ML predict routing congestion before the routing process begins, enabling the algorithm to proactively find the alternative paths. This will significantly reduce the congestions and interconnection delays and the predictive modeling and analysis. Predict Predictive modeling uses ML to force potential design challenges like timing violation, thermal hotspots, or congestion issues early in the design flow. How the ML helps is the timing prediction. A supervised learning model trained on historical designs predicts the critical path that may cause the timing issues. Thermal and power predictions. ML analyze the chip layouts and estimate the thermal and power behavior, guiding the optimization before they tape out. Uh, Power optimization and leakage reduction. Power efficiency is crucial aspect for especially for mobiles and IoT devices. ML assists in analyzing and optimizing power consumption while minimizing the leakage. Power analysis models, ML models predict power hotspots by analyzing usage pattern, component placement, and switching activity. Leakage mitigation, ML recommend techniques like adjusting transistor size or modifying cell placements to reduce the leakage current in ideal state. Timing closure and optimization. The timing closure ensures that all signals in this design meet timing constraints such as the setup and hold times. ML simplifies this by critical path prediction. MI models identify the critical path and suggest the adjustment to placement or clock tree synthesis to meet the timing requirements. Dynamic timing adjustment reinforcement learning dynamically modifies routing paths or delays to achieve the timing closure. Uh, Design rule checking and physical verification. Design rule checking ensures that the chip layout address to manufacture design rules, while physical verification confirms the functionality and performance. This process are often bottlenecks in the design rule. How the ML helps is it automates the rule checking. ML automates the identification and correction of the DRC violation, reducing the manual workload and pattern recognition. Convolution neural networks detect common layout violations such as spacing errors or misaligned features with a high precision. Accelerated physical verification. MI models simulate real-world conditions to verify the chip performance under different scenarios quickly. AI assisted design automation. AI assisted design automation represent a transformative approach in VLSI by integrating the AI into various stages of the physical design flow. This allows for smarter, faster, and more efficient optimization of chip design. Intelligent floor planning and placement. What it involves is floor planning involves arranging the functional blocks on the chips, while placement aligns the exact location from for standard cells and macros, which is blocks. AI enhance this process by automating the decision making and improve the efficiency. Enhancing the formula, AI algorithms analyze the chip requirement and suggest optimal arrangement of function blocks to minimize the power and delay. AI model can especially reinforcement learning dynamically explore and determine the best placement strategies to reduce the congestion and violence. AI-driven global routing. Routing connects the placement components using metal wires across multiple layers while avoiding congestion, minimizing delays, and adhering to design rules. Uh, Congestion prediction. AI models analyze the placement data to predict potential routing hotspots and suggest changes to avoid them. Routing optimization. AI explores multiple routing paths simultaneously, uh, choosing that ones that minimize delays and power consumptions. Automated clock tree synthesis. The clock tree synthesis is the process of distributing the clock signal uniformly across all components to minimize the speed and ensure the timing accuracy. AI optimizes the process by automating the clock tree synthesis. Clock skew minimization. AI analyzes the chip layouts to design the clock trees that minimize the skews. They adjust the clock tree parameters dynamically to balance the timing, powers, and area. Um, AI identify the strategies to reduce the dynamic and static power consumptions in the clock network. This produces high quality clock distribution networks with minimal manual intervention. AI-based decision-making tools. It involves AI-based tools assist the engineers in making the uh, informed decision by analyzing a complex trade-offs in real life during the design process. AI tool elevates the design constraints and provide a recommendation for floor planning, placement, and routing. AI analyze the power, performance, and area metrics to suggest the best optimization strategies. AI learn from the past designs to anticipate challenges and provide actionable solutions. Automated physical design verification and DFM was designed for manufacturing. Physical verification ensures that the design complies with manufacturing rules, while design for manufacturing focus on making the design manufacturable with high yield and reliability. AI automate this process to reduce time and effort. AI identify rule violation faster and suggest correction. Pattern recognition for the from AI analyze the common yield limiting patterns and recommends layout adjustment to improve manufacturability. AI stimulate the manufacturing process to predict the yield and optimize the design for higher reusability. AI or ML techniques in physical design automation. Bayesian optimization. So first, optimization is a problematic model-based optimization technique, right? Primarily used for fine-tuning the design parameters in a way that enhance the power, performance, and area of a chip. It particularly uses when the design space is large and the evaluation of each design point is costly, such as formulating or manufacturing design. So how it works is it uses models to approximate the expensive to evaluate object of function such as PPA. It then uses an application function to guide the exploration of the design space, balancing between exploiting regions that have previously yield good result and exploring new potential better areas. In PDA, this technique used to adjust the various design parameters. It iteratively improve the overall chip performance. Uh, Convolutional neural networks. CNN that are class of deep neural networks, particularly effective for tasks involving image and spatial data. In physical design automation, CNNs are used for pattern recognition in chip layers. How it works is feature extraction. The CNN excel detecting the hierarchical pattern in visual data, which makes them ideal for recognizing patterns in complex chip layouts. They can identify key features such as placement of gates, interconnects, or potential design flaws in the layout. Layout analysis in PDA, the CNN can be applied to detect issues like congestion region, placement violation, or potential routing problems easily in design process. Reinforcement learning. Reinforcement learning is the AI technique that optimizes the multi-step decision-making process by learning from interaction with the environment. It used to optimize the flow of process like placement, which involve many sequential decisions. That how it works. In reinforcement learning and the AI model is make decision based on its uh, current state and receives the feedback based on the effectiveness of the action. The oral agent explores various placement and routing strategies while learning with strategies optimize the design objectives. Oral can be used for automating and optimizing the complex stuff for chip placement and routing. It can handle tasks that involve making decisions based on long-term outcomes such as reducing noise or optimizing power consumption across multiple stages of the chip design flow. Transfer learning. Transfer learning involves using knowledge gained from one domain or task and applying it into another related task. In theory, the transfer level is used to leverage prior decision knowledge for new project, particularly when the design shares similarities with the previous design chips. Pre-design model. Transfer the learning typically involves using a pre-trained model such as CNN or oral model that was initially trained on the related design task and then fine-tuning it for the specific requirements of a new project. This model is adapted to the new design space and leveraging the previous experience from a similar task to speed up the learning process and improve the decision process. Example, using a model trained on the sets of chips with similar layers and constraints, applying it to a new project that shares similar routings and placement characteristics, and fine-tuning the model for the new project-specific needs. Application of AI or ML in physical design optimization, placement optimization. The purpose is the placement optimization, which it involves determining the optimal location for different components. Example, logic gates, cells, or the chips, to minimize the violence and reduce the conditions, which ultimately improve performance and manufacturability. The machine learning models, ML, such as supervised learning algorithms, can be trained on historically placement data to predict the best location for various cell based on factors like timing, powers, and area. This model can recognize patterns from past designs and can apply them to the new design. Violence reduction by positioning components strategically, ML algorithms helps to reduce the total wire length required to connect the components, which improve the signal propagation times and reduce the power dissipation. ML model can make more accurate and efficient placement decisions than traditional heuristic, leading to better chip performance, a lower power usage, and more manufacturable designs. Routing of automation. Uh, Routing in chip design refers to the process of connecting the different components, cell gates, using the metal layers, ensuring that electrical signal can travel from one part of the chip to another without causing signal integrity issues or timing violation. A model can be used to automate the routing process uh, by learning from large data sets of successful routing patterns and then applying these patterns to new designs. AI algorithms can ensure that routing to timing, powers, and signal integrity constraints while learning how to prioritize routes that meet these requirements. It can predict the potential routing problems like crosstalks or signal delay and allowing the designers to optimize the routes before manufacturing. Uh, Automating the routing that accounts for timing and power constraint, ensuring the best paths are chosen for signal connections. Uh, Example, AI-driven routing that optimize the signal paths in a processor, ensuring that time constraints and signal integrities are met without manual intervention. Analysis and closure. The timing analysis ensures that the chip meets the required timing constraints such as propagation time for signal between the logic gates. Timing closure is the process of iteratively adjusting the design to meet all timing constraints before fabrication. Uh, uh, MI algorithms can predict potential timing violation earlier in the design cycle, allowing designers to make adjustment before physical design iteration begins. It can automate the analysis of timing faults and identify the critical timing issues that might affect the chip performance. Uh, by learning from past design, these models can suggest optimal changes to address this issue. A by MI algorithms that predicts where the timing issues might occur and suggest adjustment to timing pods or gate delay to achieve this closure. Power optimization. Uh, Power optimization in chip involves reducing the overall power consumption of the chip with a critical for battery power devices, heat dissipation and performance. ML can analyze the design parameters and predict power hotspots, areas where the power consumption is likely to be high, allowing the designer to address the potential power issues early in the design cycle. AI can assist in optimizing the layout, placement, and routing of components to reduce the power consumption. For example, it can predict which components should be powered down or which routes should be avoided to minimize the power leakage. Dynamic power management, reinforcement learning can be used to develop dynamic power management strategies that adjust the power level based on usage patterns and optimizing the energy consumptions over time. Uh, then the benefit is by using the AI to uh, predict and manage the power usage, the design process becomes more energy efficient, leading the chips that consume less power and generate less heat and have a longer battery life. Example, AI model predicting which region of processor chip which will consume the most power and suggesting the design changes to reduce the power draw, such as relocating high power components or applying the uh, voltage scaling. AI and ML in EDA tools. Integration in tools like Synopsys, Cadence, and AI and machine learning are increasingly integrated into electronic design automation, that is EDA tools, to enhance the uh, performance or automate tasks and accelerate the chip process. Uh, the key application of AI and ML in leading EDA tools like Synopsys OpenRoad includes timing optimization using ML. The ML model for timing analysis, timing optimization in simplification to ensure that the signal propagate correctly within the required timing constraint. MI model in EDA tool can analyze the larger data sets of timing paths and historic designs, identifying the pattern that helps to help optimizing timing across various stages of the design. AI can predict the timing violation before running extensive simulation, allowing for faster identification of potential issues and speeding up the timing process. Uh, AI for space exploration. Uh, EDA tools EDA tools integrate AI and ML to explore the design space more efficiently. Traditionally, the design space is vast and required numerous simulation and iteration to find the optimal design. AI helps to reduce the number of design iteration needed by identifying promising regions of the design space based on previous knowledge. It can explore trade-offs between the design parameters such as power more efficiently suggesting the optimal configuration. By learning from previous design iteration, AI model can recommend design adjustments and application in Synopsys and Cadence. AI is integrated into Synopsys tools to optimize the PPA, improve static timing analysis, and enhance the physical verification. In Cadence, the ML algorithms focus on optimizing the routing, reducing the conditions, and improving the L prediction for better performance. Open road role. Open road is an open source EDA tool designed to automate the RTL to GDS flow, offering numerous AI capabilities to improve the physical design processes. Uh, AI AI-enabled routings and condition analysis. AI-powered routing. Open road leverage AI for routing optimization by analyzing routing conditions, identifying regions that need adjustment, and suggesting the best routing paths. AI models helps ensures that routing constraints are met while minimizing delays and power consumption. AI can predict areas of congestion before it comes an issue, allowing for early adjustment in the design process to ensure the smooth routing without signal interference or extensive delay. Machine learning for signal integrity. AI algorithms also helps analyze signal integrity by predicting the crosstalks and other interference issues in the routing process, helping designers to avoid potential failures in the chip performance. uh, Fully automated RTL to GDS flow. End-to-end automation. Open Road supports the fully automated RTL to GDS flow, which means that the entire chip process from RTL coding to the final GDS layout is automated using AL and ML algorithms. This drastically reducing the times and effort needed to manually configuring each step. Within the fully automated flow, AI-driven tools can optimize various aspects such as placement, routing, clock tree synthesis, and timing closure, all in a highly integrated manner that results in faster design cycles and more efficient use of processes. Application in the open road, AI in open road helps to automate the placement decision based on historic data and optimize the component. Challenges used in AI and ML for the physical design automation. While AI and ML techniques offering significant improvements in the PDA process, their integration and practical application face several challenges. The challenges must be addressed to ensure the effective use of AI and ML in chip design. Data availability. Need for a large and high quality data sets for to train the ML models. The challenges for machine learning models to perform well in PDA, they need to be trained on vast amount of data that accurately represent the design space. This ensure a high quality design data such as timing, routing, PPA metrics from previous sub-design. What the problem is gathering a sufficient volume of high quality labeled data sets can be challenging, especially in industries where design data is uh, closely guarded. Without access to which diverse data sets, ML models may struggle to generalize and provide reliable results. The solution is developing a standardized data sets from a variety of sources, including both open source data sets and collaboration across industries can help this challenge. Simulation-based approach can also be used to generate synthetic data uh, to train the data sets. Example, AI model trained on a specific set of chips might perform poorly on the new design with a different specification or constraint, or because the data used for training does not cover the design unique features. Generalization is AI model trained on one design may not generalize well to others. Machine learning model, especially deep learning models, tends to perform well on the data they were trained on. However, they may fail to generalize to new or unseen designs with different characteristics, leading to suboptimal performance in real-world scenarios. Uh, the problem is that every chip is unique with different design specification, constraints, and requirements. A model that was trained on a specific design or set of designs might not be applicable to another design, making the transfer of learned knowledge is difficult. computational overheads, high resource consumptions for training complex ML models. ML models, especially deep learning models and reinforcement learning, require significant computational resources for training. This includes powerful processor, large memory, and specialized hardwares like GPUs. Uh, Training a complex AI model can be time-consuming uh, and costly. For instance, training a deep learning model to optimize the timing or placement across multiple design scenarios could take days or even weeks, depending on the complexity and the size of the data. Solution to get the computational overheads more efficient can be used to reduce the size and complexity of the model. Example, training a reinforcement learning model to optimize placement and routing in chip design might require using multiple GPUs over the course of several days for smaller companies or startups. This could be a significant barrier due to the hardware limitation. Industry impact of AI or ML in PDA. Faster time to market. AI and machine learning technologies are revolutionary chip design by significantly reducing the time needed to complete the design cycle. Traditionally, chip design is a complex and iterative process that involves many steps, including the placement, routing, and verification. AI helps to streamline this process by automating repetitive tasks, predicting design outcomes and identifying the potential issues earlier in the process. This results in faster prototyping and quicker time to market, allowing companies to deliver products more efficiently. Advanced node design with semiconductor technologies shrinking to smaller nodes such as 5 nanometer and 3 nanometer, designers face increasing challenges related to power performance and area. At, at the smaller nodes, transistor density increases and physical constraints such as leakage current, power consumption, and heat dissipation become more significant. AI and ML algorithms can used to predict and optimize various key factors. At this advanced nodes, machine learning can predict the areas of congestion, power hotspots, and potential failures which can be mitigated during the design phase. Energy efficiency plays a crucial role in optimizing the energy efficiency of the chip, which is particularly important in the context of IoT device and edge computing application, where power consumption is a key concern. ML model can predict power consumption patterns early in the design cycle and suggest design optimization to minimize the power usage. For example, AI-driven tool can identify areas where optimization techniques such as clock gating, voltage scaling, and power-aware routing can be applied to reduce the overall uh, power consumptions. This ensures that chip meet the energy efficiency requirements of modern device without compromising the performance. Uh, Case studies in AI and ML for PDA. Google reinforcement learning for flow planning. This is the Google used for reinforcement learning in optimizing the flow planning for their tensor processing units. TPU is a great example of AI or ML being leveraged in the design of specialized hardware. In oral, the algorithm learns from experience, progressively improve the placement of the component on the chip based on the feedback from the system performance. The algorithm searches for optimal component layout that minimize interconnect lengths and optimize power distribution and improve the chip performance. RL can enable Google to set up the storing floor planning process, optimizing designs that are more efficient and less power hungry, crucial for high performance chips like TPUs. NVIDIA's ML based timing analysis. NVIDIA approach to using machine learning for timing analysis showcase how AI can significantly speed up and improve the accuracy of timing cluster execution. Traditionally, timing analysis involves verifying the timings of every signal pods in the design, ensuring that all signal arrives at the destination within the specified timings. Machine learning models are able to predict timing violation earlier in the process and can help identify potential problems areas long before the final decision is completed. This predictive analysis accelerates the timing cluster, reducing the risk of lost state design rework and improving the overall design efficiency. Additionally, this helps to ensure that the chip meets the performance specification before chip implementation. Open road contribution. Open road is an open source project aimed at providing a fully automated RTL to GDS flow, integrates AL and ML for various tasks, including the routing, placement, and congestion analysis. AI-driven algorithms are used in open road to tackle the challenges such as congestion, which occurs when the layout becomes too dense, leading to poor performance and manufacturability. Machine learning models analyze past designs to predict and mitigate areas of congestion earlier, and while other optimizing the placement of cells and routing first to achieve the best possible performance. Open road integration of AI makes it an invaluable tool in modern cities, reducing the need for manual intervention and enabling a more efficient and scalable design process. Future trends in AI are ML for PD. AI-driven full stack design automation. Looking ahead, AI is drive full stack automation across the entire chip design process, from the high-level architecture stage all the way to tape-out. Full stack automation means that AI will be integrated into every stage of the design flow, from system level modeling and design exploration to placement, routing verification. AI can analyze the design specification and automatically select the most suitable architecture and design methodology at every step. This reduces human interventions and minimizing the errors and speed up the design cycles, ultimately allowing for the creation of better design and faster collaborative AI. As design problems becomes increasingly complex, the future of AI is in chip design involve collaborative AI where multiple AI agents work together across different domains. This agent each optimized for specific task. This collaborative approach enable cross-domain optimization where the design process can balance competing objectives more efficiently. Collaborating AI system could adaptively adjust to their strategies based on the evolving needs of the design, leading to more efficient and balanced chip layouts. Uh, quantum computing and AI are both advancing rapidly, and a combination of tools could significantly change the landscape of chip design in future. Quantum computing has the potential to solve optimization problems that are too complex for classical computers, making it well suited for tasks like design space exploration and complex multiple objective optimization. By integrating AI with quantum computing, designer could tackle the challenges in chip design that were previously thought to be such as optimizing chip layers for quantum process or solving problems in a very large scale design. As quantum computing measures its could help the new possibilities of for AI to future optimizing the design of future chips, particularly in the field of quantum computing itself. The benefits of the AI is enhance the accuracy and efficiency. That is, it is in the chip design by analyzing the vast amount of data from past designs and applying this knowledge to optimize the current project through current projects. This technique like predictive modeling, AI can provide more accurate for timing, power, and congestion issues. The automation of the routine uh, tasks like placement, routing, and verification means that engineering can focus high-level optimization while AI handles more error-prone tasks. This results in faster and more accurate and more reliable design. Reuse with manual intervention. AI-driven tools reduce the need for human intervention by automating key design process. For example, AI can automatically optimize routing to reduce the congestion, improving the timing and ensure the signal integrity. While deep learning models can predict the best component placement for optical power uh, by offloading the task to AI, engineers can focus on high-level design decisions, improving the overall efficiency of design team and reduce the chance of human error. Faster convergence on design goals. Uh, Machine learning models can quickly assess the large design spaces and identify optimal configuration, ensuring that the design process reaches its goals more quickly. AI can also predict potential bottlenecks or issues, helping the design team address this early on and refine design towards its final optimized form. Uh, this means that the design process is more predictable and less likely to experience costly delays. Uh, Demonstration of chip design. AI and ML has the potential to democratize the chip design by making advanced design tools uh, uh, more accessible. Open source initiatives like OpenRoad allow company startups and academic institutions to use powerful AI-driven design tools without a heavy cost of traditional commercial EDA tools. This enables smaller companies or resisting to participate in the chip design process, leading to more innovation and diversity in the design community. Comparison of the AI-enabled PDA in Synopsys. Synopsys offers a range of AI-powered tools for optimizing the performance in the chip design. Their predictive time analysis uses machine learning to anticipate timing issues earlier in their design cycle, helping engineers identify potential violations and fix them before the design process is complete. This predictive capability improves the accuracy and speed of timing pressure, ultimately reducing the time spent on manual rework and ensuring that design meets the requirement. In Cadence, the Cadence has integrated deep learning techniques into their design tools, particularly for placement optimization and congestion-aware routing. This tools analyze the chip layers and adjust the placement based on the real-time feedback, reducing congestion and improving the overall design efficiency. Cadence AI-driven routing optimization ensures that signal paths are efficient and the timings and the signal integrity requirements are met, making the tools valuable for complex and high-performance designs. OpenRoad is an open source tool that it incorporates AI algorithm for conditions and time analysis, ensuring that the design process uh, is as efficient as possible. OpenRoad's AI-powered features optimize various design aspects such as uh, routing, placement, and timing by analyzing a large data sets from previous design. This results in better PPA outcomes and a more streamlined design process, which benefits the entire chip design ecosystem. OpenRoad transforming the physical design automation. What is OpenRoad? The OpenRoad is an open source EDA tool chain designed to automate the RTL to GDS. It is specific. specifically crafted for optimizing and streamlining the chip design process, offering a complete solution for physical design tasks like placement, routing, and timing analysis. OpenRoad aims to democratize the access to very large scale integration design by making powerful tools available for free, supporting both academic research and industry needs. Um, Open Door ultimate goal is to create a robust platform that can be used by anyone from academic institution to startup company for efficient scalable citizen. Key features of the Open Road end-to-end automation. Open Road automates the entire physical design flow from RTL to GDS, making it an end-to-end solution from chip layer. The platform supports the key stages in the design process, including the whole planning, placements, clock free synthesis, routings. By automating these steps, OpenRoad reduces the manual effort involved in the chip design, accelerates the development cycle, and minimize the human error. Uh, AI/ML integration. OpenRoad incorporates AI and machine learning techniques to optimize and enhance several parts of the physical design process. Their data-driven approach are integrated into critical tasks like condition analysis and timing optimization. The use of AI allows for smarter decision making, enabling more accurate prediction of design behavior based on historical data. For example, machine learning models are used for placement optimization to reduce the erosion and improve the overall efficiency of chip design. Uh, uh, and last, a community-driven development. As an open source platform, OpenRoad encourages contribution from the global design community. It has become a collaborative environment for designers, associates, and developers to experiment with new techniques, share innovation, and solve complex challenges. The community-driven nature of OpenRoad enables the rapid incorporation of state-of-the-art integration and also ensures that the tool chain remains flexible and adaptable to changing the industry needs. AI and ML in OpenRoad. Placement optimization using the OpenRoad leverages ML to improve placement quality, which is crucial in minimizing violence and reducing congestion. By using ML algorithm, the system learns from past design data and can predict optimal placements that lead to more efficient design. Uh, this leads to better performance, lower power consumption, and reduced design as the placement process become both uh, faster and more accurate. Routing and timing analysis. AI and ML can use to accelerate timing cluster and ensure signal integrity in the design process. By analyzing historical data, machine learning models can predict potential timing violations before they occur, allowing designers to address issues proactively. Uh, Data-driven enhancement. Uh, OpenRoad AI capabilities extends beyond individual optimization. It uses data-driven techniques to analyze the patterns and trends from past design itself, just to make it modernization about design improvements. By analyzing historical design data, OpenRoad can suggest design modification that could enhance performance optimization over and reduce area, thereby providing valuable insights throughout the design cycle. Why OpenRoad is unique, fully open source. Unlike tools such as Viado or Cadence, OpenRoad is entirely open source. This make it cost-effective and accessible options for researchers and anyone looking for to contribute concepts and OpenRoad enterprise access to powerful EDA tool, allowing a wider range of people to participate in VLSI design without the barrier associated with expensive software. Designed for scalability, OpenRoad is designed to scale effectively across different process nodes, including advanced technologies uh, like 7 nanometers and beyond. As semiconductor fabrication continues to push the boundaries of Moore's law. Open road scalability allow it to use to for cutting edge techniques, ensuring it remains relevant as industry evolves. This scalability is critical for ensuring that chip, chip design meets the performance and density requirements of future generations, accessible for platform for experiments. Open road workflow. The input of the open road toolchain is typically an RTL design written in Verilog or VSTL. The RTL code represents the functional description of the chips, serves as a starting point of the physical design processes. Uh, Open road automates the various stages of physical design flow, including floor planning, where organizing the layout to ensure optimal area utilization. In placement, determining the position of the cells on the chips. In clock tree synthesis, creating an optimal clock network to ensure balanced timing. In routing, the interconnection between the placement components. Lastly, generating the final CDS layout file, which is ready for manufacturing. Out, uh, output of the open road tools is the CDS layout, a standard file format used for manufacturing semiconductor chips. This file contains the final design, which is then sent to fabrication facility for production. Uh, The benefits of open road in PD accessibility of open road is a free open source solution that lowers the barrier to entry for chip design. Designers can access the tool chain without the need for expensive license, making it an ideal choice for startups. Customization open road is flexible and can be customized to integrate with the AI and ML for experiment and optimization. This means that the companies and researchers can uh, tailor the tool set to specific needs, allowing for cutting-edge experiments and custom solutions. Efficiency. By automating many of the complex and time-consuming tasks in cities and open source helps to reduce the design cycle times and improve the overall efficiency of the design process. With its AI or ML enhanced capabilities, open road speed up tasks like placement, routing, and time plus, helping the designer to meet the deadlines and produce the high quality designs in less time. I will show you how the final layout will be present in the open road. This is the open road close to inside this open road close to flow directory only. The our designs will be there. Uh, uh, Here in the make file only, the uh, designs that RTL code that we have written, it will be there. Using the command VA make file, we can open the make file. Uh, we can see that several designs that were already present in this make file. Uh, it's like a default design, which is when we install the open road, there will be a default design called mandate using a GCD. Its technology is mandate 45, and now we are going to run a design microwatt. In this, if you want to run design, means you have to uncommit the time design which we are going to run. and after that we have to save it. Um, Once you choose the in the make file which file you are going to run, after that we have to run the make command. Uh, it will run all the process as I had said that the floor plan steps, placement, routing, all the steps it will automate just by one click, one command. It will automate the whole process. As I have already run, so it has run in few seconds. If you are going to run for the first time means, uh, based on your design, it may take 10 minutes to some hour also it can take. If you want to see your final layout means, the command is make GUI final. This will the final layout of the TDS layout that is ready for fabrication, which is this design is the microwatt, which is also an open source that is developed by an IBM, which this design is also available in the open door close scripts. And, this is the final PDF layout of the microwatt. Here you can see several metal layers based on your technologies. Metal layers will reduce when the nanometer size increases, the metal layer gets reduces. For this microwatt, it has used SKY 130 nanometer, so the metal layers is 5. Where the first metal layer is used connect the standard cells. So and the fifth layer is also for power connection. The rest cells will arrange in first cell, and the fifth cell will be arranged in vertical, uh, horizontal, and the remaining is in vertical direction. Mm. Here you can see the scripts. Currently, we are designing Skyward 130 to go into that. Here only our constraint file and config file will be present for the current technology report we have written. Likewise, we have to, if you want to create your own RTL code also, we can create it, and you have to give the required constraint file and config files. After you have created your code and represent, given the correct constraint and config files, we have to mention it in the make file which I had shown earlier. Here, you had created a new design on your own, which technology you have used. For example, if you have used in AND gate 45, you have to create your design under here in in which path it had been created, in design which technology you had used, and what name of the project you had used. And the config of in this config, see the location of each file, that how the code is written and how it's working. So here I have gone to the result directory. It will show the each result in a separate database of each step-by-step process. It will store the database here. In the result directory, I have using the technology called Navigate. In this, I showed that it shows each stream separate database file for floor plan in the floor plan for macro placement and tab cell and power distribution. In placement, there will be people called global placement and detailed placement, the steps and clock trace interface, routing, and at last the our final layout, which will be in this file 6.v. If you want to open in between the steps, and if you want to change anything also, you can do it. For example, you want to see the global placement script. Here you can see if you want to change anything before this means we have to go to the required script and we have to change it accordingly. But this workload here, it will automate the full flow from RTL to VDS. If you want to change anything, means you can do, but it is a fully automated. Uh, we'll come to a conclusion. AI and ML are transforming the landscape of physical design automation by solving complex challenges related to the design optimization, timing, and resource management. These technologies are enabling a faster and more efficient design by automating traditional labor-intensive tasks like placement, routing analysis. The integration of AI and ML into the tools like OpenCode, Synopsys, Cadence is already helping engineers and designers address the growing challenges in modern semiconductors. Uh, Takeaways, growing role of AI or ML as its design becomes more complex. AI and ML will continue to evolve and expand, providing intelligent solutions for increasingly uh, uh, from optimizing placement and routing to improve power efficiency. AI-driven tools will be crucial for meeting the demands of advanced process like most examples 7 nanometers and beyond. The ability of AI and ML model to automate the various states of the design process will significantly reduce time to market and making it possible to rapidly iterate and deliver products in a shorter time frame, which is critical in today's competitive and hostile technologies. I have finished my presentation.
Participants, any
If you
queries?
have any queries, means you can be curious about.
Hello, sir. Is its guide available on the site? Open Road, how to work with Open Road?
Yes, it is a purely open source only research, so it is available.
And sir, we can implement this Open Road on Linux only or Windows-based also operating system?
Oh, Windows, you can have one tool which you can install that will work as a Linux. In those system also you can work, but you have to install
Oh,
the tool.
okay, okay. Right. Thank you, sir.
Sir, one question in chat box, sir. How AI can use in reducing dynamic power? Can you explain with some examples? Kripanidhi, sir. Hello, sir. Can you hear me?
Yes, uh, I did not correctly, I am not, I, not correctly working that I will see and do.
Okay, sir. Okay, sir. Any other queries, participants? We have 10 more minutes to discuss. Okay, if you don't have any queries, we can end up the session. Triveni, ma'am.
Sir?
Can we end the session, ma'am?
Yes, sir. Yes, sir.
Okay, ma'am.
Farhan sir is said to join, I
Yes,
hope.
yes, ma'am. Yes, ma'am.
Okay.
Kripanidhi,
Participants,
sir,
please
thank you
be.
so much, sir.
Uh, Thank you.
Thank you, sir. Thank you.
Thank you.
Participants, please wait for 5 more minutes. Sir will be joining in short. We have one more session, session 6, which will be handled by Farhan Yazdani sir. So he will be joining the session now. So many of you are going out of the meet. So one more session is there, that is session 6. Please wait.
Participants kindly wait. Sir will be joined in 2 minutes. Fargan sir, welcome you sir.
So, good evening, sir.
Unmute. Good evening.
Yes sir.
Good evening, sir.
Good evening, sir.
Good evening sir.
Welcome, sir.
Ma'am, shall we start the next session, ma'am?
Yes, sir. Yes, sir.
Okay, ma'am. A warm good evening to one and all co-present here. On behalf of PSNA College of Engineering and Technology and Department of Electronics and Communication Engineering, we welcome you all for the Day 3, Session 6 of ATAL sponsored 6-day online faculty development program on artificial intelligence techniques in VLSI design. Now I kindly request Dr. M. Triveni Madam to introduce the Session 6 speaker, Dr. Fargan Aljadi, sir.
Thank you, sir. Welcome, Farhang sir.
Thank you. Thank you.
For, let me introduce you, sir. Farhang Yazdani is the President and Chief Technology Officer at Broadpack Corporation, a provider of advanced 2.5D and 3.5D heterogeneous chiplet integration technologies and design or manufacturing services based in San Jose, California. Through his 22 years in the industry, he has served in various technical management and advisory positions with leading semiconductor companies worldwide. He is the author of the book Foundation of Heterogeneous Integration, an industry-based 2.5D or 3.5D pathfinding and co-design approach. He is the recipient of 2013 NIPSIA Award in recognition of his contribution to the advancement and innovations in packaging technologies. He has numerous publications and IPs in the area of packaging and assembly, serves on various technical committees, and is a frequent reviewer for IEEE Journal of Advanced Packaging. He received his undergraduate and graduate degrees in chemical engineering and mechanical engineering from the University of Washington, Seattle. Broadpack is a provider of advanced heterogeneous chiplet integration technologies and design manufacturing services based in San Jose. The company leverages its industry-leading world-class expertise and proven packaging technologies to create competitive packaging solutions for its clients. It supports global clients in networking, communications, medical, aerospace, and consumer electronics. His role as president, he oversees the operations of Broadpack Corporation, focusing on strategic growth, business development, and fostering a culture of innovation. As CTO, he leads the company's technology roadmap, working on cutting-edge developments that enable Broadpack to provide state-of-the-art solutions to its clients. He is known for his strong technical leadership and ability to navigate the complexities of fast-paced high-tech industries. His expertise spans across multiple domains, including semiconductor packaging, electronics, advanced technologies, positioning him as a key thought leader in his field. So we are happy to have a person like Farhang sir with us. Sir, the session is yours. We are feeling very happy to be with you for the next 1.5 hours. Thank you, sir.
Well, thank you so much for the introduction. It's a pleasure to be part of this event. Let me find a way to actually share the presentation
Yes, sir.
on this thing. I hope you can see that. You can see the slides. It should
Yes, sir.
be visible. Yeah,
Visible, sir.
let me put yeah, let me put it in the screen mode. Oops, this makes it okay. Is this better? Should
Can
be
you
full
share
screen.
in full screen, sir?
Yeah, this is full screen. It seems like when you put it, is this better?
Yes, sir. Okay, sir.
It's okay. Yeah. So, so thank you again for the intro. It's a pleasure to be part of this event. My focus of talk is going to be more on the hardware side and what are the requirements and how we're going to build some of the advanced packaging and the system level integration required for building an AI systems. So there's a lot of items to share and talk about, depending how much time we have. But here's a brief outline of what I'm going to be talking about. It's going to be, I like to talk about the market megatrends. That's very important to us. We're going to have to understand how the market is evolving and then how the memory logic and the hardware is going to be aligned with the market trend. I'll then dive into the foundation of packaging. Packaging is the building block of this system level integration and is very critical. It's going to impact the cost, the performance, and the overall success of the program. I'll then talk about the emerging chiplets and the heterogeneous integration, what that is and what are the requirements. I'll then talk about some of the packaging technologies. We'll get to that. I'll talk about the advances in the substrate. Substrate is the foundation of the IC packaging and directly influence the cost and the performance. So it's very important. And then I'll talk about some of the fabrication processes to manufacture these type of packages. And if time left, I'll talk about the design, tool flow, and the methodology for this type of design, and then I'm going to wrap it up. So, as well as it was mentioned in the in the intro, here's the book on the heterogeneous integration. I strongly recommend to get it, or it might be available at the library, at the universities. Is already at 200 plus universities worldwide. Is very hands-on, nothing theoretical. Is hands-on, explains in detail with practical examples how to do this type of integration and design. And and it's good be a very good resource. So I would say this is the starting point to further learn about this thing. So so let's talk about the mega trends in the packaging evolutions. If you look at what the TSMC chairman said back in 2011, that's quite some time ago. I mean, the TSMC and the semi industry, they could see the limitations of the monolithic integration. And again, as the Dr. Morris Chang said back then, is that the Moore's law will meet its limits by 2020, which we will at which point we simply will not be able to shrink the transistor anymore. And that's exactly what happened. We are getting into the chiplet era. A new way to do the system level scaling for these type of devices. And they said back then that TSMC has invested significant R&D into 3D chips, and they call it the system level scaling. All right. So they could see that this is coming. So even back in 1965, the papers by the Moore's law by Dr. Moore actually, this is the direct quote out of the paper back in 65, that it says directly, it may prove to be more economical to be a large system out of a smaller functions, which are separately packaged and interconnected. All right. And the rest you can go through that. So this is what it means is the chiplets and to build a smaller unit and is how to scale it up. So according to Dr. Green of DARPA, heterogeneous integration was part of the Gordon Moore's master plan the whole time. No need to worry about the end or changing the name to More Than More, right? So so let's talk about the mega trends. One of the things that we saw, many years back, everything moved into the cloud computings. However, with the advent of the AI and the response time required, it would be difficult for the edge devices to communicate with the cloud because it could be life-threatening and very critical to be able to do the computing on the edge. So the mega trend was that we did it on the cloud. We then moved it to the fog computing, and now we are designing and building AI system for the edge compute. And the edge compute has got its own challenges, right? The real estate needed to integrate, the amount of power, scaling, size, all of that is going to be important. So each of these cases has got its own challenges to be able to build a system for. So AI, again, is nothing new. It's been around for 65 years or so. And the reason that we are seeing it more is that because the data is available, we got the computing and the machine learning resources also available, and the connectivity is also available. So now we can do this type of pattern recognition. So AI is basically to recognize the pattern and let the machine to detect the pattern for us based on what it's been trained for. The other mega trend was the rise of 5G and 6G, which is an enabler. And of course, as we increase the bandwidth, the communication bandwidth is going to accelerate the global obviously growth, is going to bring the IoT, AR, VR to the mainstream, is going to enable the edge compute, AI plus 5G. Now you have a new stream of a product and good sources of the revenue, reduces the cost and increases the profitability for the consumers. Now, the most important mega trend here is the shift in the computing, which is the memory and the logic. So if you look at your old house motherboard, which could still be out there, you see that you got a processor and the memory that is sitting on a PCB. So these are two separate packages communicate through the PCB. Due to the huge amount of the memory required for the AI and the edge compute, the memory instead of the PCB actually moved into the package. That means we co-package the memory and the processor in just one single package. So now you got your I would say memory or the device here that is going to communicate with the other I would say memory component, which is mounted right next to it on the same package, meaning we're going to shorten the communication pathway between the logic and the memory. That's where things are. Now, now to increase the memory bandwidth, this is the high bandwidth I would say memory. You'll notice that the DRAMs are being stacked and connected with the TSV right through that. Now, the next step beyond this thing is going to be in-memory compute. That means why not bringing the memory directly to the logic layers and stack it up and do the memory compute. And of course, this has got its own challenges and is in the area of the research. Number of startups are working in this area, but is an emerging area as well. So, so the packaging. So how we package the thing is going to be important. And let's get an overview of the packaging evolutions back in the 70s and 80s. You know, things were much simpler. We had the dual inline package, QFP, SOP, and pin grid array. I'm sure you've seen some of the older Pentium processor or you know other packages that they had pins on it. In the 90s to 2K, you know, we moved into the what is called the BGA, the bulk grid array, and the QFN and the chip scale packaging. And then from 2000 to 2010, we then started to build some of the dies on the same package. We call it the system in a package. We then started to stack the packages in 3D. We call it the package on package. We also started to do some of the wafer level packaging. I'll explain what that is later on. And then we got into the fan out packages. So take this terminology for now. I will get into explaining what these things are later on. And then 2010 to now, we're shifting toward the 2.5D, 3D, integrated fan out, 3D info, and PLP. So things are emerging. These are all good stuff. And of course, the choice of packages is driven by the market. For example, for the mobile, you know, the package got to meet a certain form factor. It should be ultra thin. You got a 5G, and then it could be a system in a package, something to do the edge compute within a mobile space where there is no airflow. So the power consumption, the form factor, all of these are going to be super important. Or for the wearable or the IoTs, again, the form factor, the security is going to be important, including the power consumption. For the auto industry, the way we package it, the reliability is super important. The MEMS, the sensors, the 5G, the autonomous, type packaging, all of these are going to be important for the auto industry. For computing, when we package, we strive for the performance, including thermal, power, integration, how we integrate those, and the reliability. And of course, for the AI and the big data, the packaging is going to require high performance. We need to do some of the 3D stacking, meaning to stack the memory dies probably on the top of the compute die to increase the memory bandwidth to the logic. The reliability is important, and then how we integrate that is also going to be important. So each market is got its own packaging requirement and emphasis. So let's talk about the foundation of packaging. What do we mean by package, or what is it that we have to do here? So if you look at a die, a chip or a die, we call it, you got two flavor that you design the die. Either it's going to be an area array bump. So this will be the surface of a die where you have the area on a grid that you would bump. And each of these bump could be a signal IO, or it could be power and ground. Or it could be a wire bonded die where you have a limited paths on the periphery where you would attach the wire bond and then you connect it to the PCB. So it's either this or that. Now, many of the things that we do is going to be in this area. Why? Because of the scalability, and I'll explain what that is mean actually. So the way we package this thing is that you take the die, we're going to have to design the substrate, and then we do the assembly, meaning we just put the die, assemble it on the substrate. This is called the flip chip assembly. And for the wire bond assembly, you just mount the die on the substrate, or the PCB in this case, as you can see here, and then we attach the wire to the die and the substrate, enabling the communication between the IC and the rest of the interconnect on the substrate, which is going to communicate through the BGA ball. All right. Now, what about the performance? Should we design for a wire bond type die, or should we design for a flip chip? Well, it all depends on the requirements and the performance. So, for example, here we show a typical flip chip die. Usually what you see in this type of devices, the center BGA, or the center bump is basically the supplies, which is the power and the ground. And the rest of the IOs are going to sit on the periphery, right? These are going to supply the power and the ground to the center of the die, to where the logic is. Yet on the wire bond type style, the supplies are situated on the periphery of the die, meaning if the center logic is here, you're just going to have to obviously drive the power and the supplies all the way from the edge to the center of the die. Yet in this format, the power and the ground is supplied directly to the center of the die. So obviously the flip chip type pattern is going to give you higher performance and higher, I would say, bandwidth compared to the wire bond. So many application doesn't require a flip chip pattern. A single wire bond type silicon is going to be enough, and some do. So the thing is that if your die size is fixed, what matters is going to be the bump pitch. So a typical pitch, meaning the center of each bump to bump, is going to be probably 200, 180, 150 micron, and now we are down to 120, and then 210, 55, on and on and on. So as you lower the pitch, you're going to increase the number of the bump and the IOs and the supplies to the device. For example, Let's take a look at some of the tight pitch scenario. Assuming that you have a 5 by 5 millimeter die, with a bump pitch of 200 micron, you get around 625 bumps on this die. However, if you shrink the pitch to 35 micron, you have almost 20,000 bump. Massive. But the thing is that if you're at 35 micron, how are you going to package it? Something like this, you can put it on a standard PCB type substrate or the PCB style, and you can escape and you can connect. However, if you're down to 35 micron, you cannot, because it goes beyond the technology is needed to assemble this thing directly on a low-cost type substrate. So what do we do? Obviously, we're going to need something else. So what we're going to do is that the die with the 35 micron bump pitch require a different type of substrate. And what is common in the industry is what we call it silicon interposer. And what is silicon interposer or the substrate does is going to take the 35 micron pitch and it's going to fan it out to 200 micron pitch. So you would assemble this thing right on the top of this. And now you can take your 200 micron and mount it on a standard laminate type substrate. And then you can see all we're doing, we're increasing the pitch from 35 micron. We fanned it out to 200. We're fanning it out to 1 millimeter pitch. So that's how the interposer actually works. And we can package that. So another way to roll of it, to look at it, is that the the role of the substrate is going to be very important. It's going to affect the performance and cost. And what it does, again, it takes the fine pitch. We're going to fan it out to a coarser pitch. And the coarser pitch allows us to use the current infrastructure for the assembly. So the pitch phenomena is going to be very important in the world of packaging and the semiconductor, because the pitch is going to impact your cost and the type of device that you're going to have to make. So the emerging bump pitch in the industry, we are in the 60s, 50 micron, 40, 30, 25, and on and on and on. The current bump pitch that is being packaged is in the range of 200, 180, 150, and 130 micron. So if you have a device with such a bump pitch, we're going to need an advanced interposer to be able to convert it to a industry standard pitch. And then with this type of pitch, we can convert it to the standard 1 millimeter BJ ball pitch using an organic interposer. This is the today's technologies. This is basically emerging. So as the pitch goes down, becomes tighter, the cost is going to have to increase. Why? Because now you're going to need the interposer here. If you design with such a pitch, then you just need the organic interposer and you're fine. But what does an interposer buy for me? So that's a question that we could ask ourselves. So an interposer, it could be glass, could be silicon, could be ceramic. It depends what that is. I mean, the material. An interposer is provide a super wide bus compared to today's narrow channel. So today's, I was laminate or the organic type substrate is kind of narrow. I was a limited type of line width and spacing. Yet if you go to the interposer, you get a lot more. You get a very wide bus. You can go parallel interface, and to be able to connect the devices at a much lower power compared to something like this. So one of the things is that you might argue and say, well, that's going to increase the cost. Now, keep in mind that from a cost perspective, when you do the 2.5D, the total cost is going to offset the cost of the interposer that we added. to the package. Why? It's going to lower the power, and that's going to reduce the cost of the energy consumption. It's going to result in a smaller die size and result in a higher yield. Meaning if you go to a tighter pitch and you shrink your die size, you get more die per wafer. You get a better yield. Um, and it's going to enable the use of lower cost process nodes. And then how you partition is going to reduce the number of the layers and reduces the investment for the foundries as well. So let's talk about the chiplet approach and the resources. So far, you got some idea about the substrate, the pitch, how we package it, and all of that, and then see how the chiplet is emerging. So, so the future SoCs, the way we're going to be doing it is that instead of a complex monolithic SoC, meaning having one die with some IP blocks, the future SoC is going to consist of heterogeneous integration of smaller, cheaper, independently designed dies with common high bandwidth interface, and which is going to be assembled on the substrate. So let me explain that in a figure that probably make more sense. So this is how we do the dies, I would say, right now. So you got a logic, you got some PLL and some interface like HDMI, you got, I would say, memory PHY, PCI, a must, DLL. Again, you got some more, I would say, memory interface, and this is your die. However, the chiplet, what it does, each of these things could be converted into a die by itself. And then we're going to put a high bandwidth connectivity between the components. And the advantage is that these interfaces becomes independent of the die, meaning they don't have to be at the same process node, so you can integrate it on the same SoC. So your core logic, where you do the compute, is going to be very important. It could be, let's say, at 3 nanometer nodes, whereas the DDR5, it could be 16 nanometer nodes with the same bandwidth you connect it. And with this thing, you can lower the cost. You can take advantage of the both worlds to shrink your core, to go to a lower process node, and then to reuse the IP. So one of the things that the chiplet does is basically IP reusability and faster verification time to market. These are already tested, verified component that is going to be mounted on a substrate and is going to communicate with the logic die. All right. So how you partition your silicon from a monolithic to a chiplet is going to be important. What is ongoing right now, at the I/O level, meaning at the IP, at the interface. And for that is usually at 40 micron pitch, we can do the die to wafer stacking, and this is ongoing. What is going to emerge and is upcoming is going to be partitioning at the IP block level. And if you partition your SoC at the IP block, then you're going to need an interposer. And probably we need the wafer to wafer bonding, and the bump pitch is probably less than 20 to 30 micron pitch. You can go a bit deeper than the IP block level to sub IP level. In this case, your bump pitch is going to be probably less than 5 micron. And in that case, you're going to need wafer to wafer bonding, which we call it the hybrid bonding, probably without the bump, meaning to fuse the two dies together. You can go partition deeper to the cell level, meaning now we're talking about 100 nanometer pitch, meaning you're going to have to bond the active layers. And then at the transistor level, it's going to be less than 100 nanometer pitch. Again, these are going to be active layer bonding. This is going to increase the cost significantly. So So you have to see at what point you're going to have to partition um, that is going to be appropriate for your product and application. So the other thing that is going to be important is going to be the plan for the testing. Obviously, the yield, when you partition, you go to the chiplet, you get a smaller die. Smaller die means higher yield. Um, but the yield, it also depends on the wafer level testing and before the packaging, meaning you should be able to test all of those to device before you package it. So, so how you do that? Well, the chiplet must be able to do full testing of the bare die at the wafer level without the packaging. Mm. What it means that everything needs to test, the chiplet must be fully designed into the chiplet, like a building self-tells, a BIST. So if you're designing for the chiplet, the testing, the DFT, the design for test is going to be super important. You got to tell me how you detect the good dies from the bad dies. And then keep in mind that when you go to a tighter pitch, you got challenges with probing of the very fine pitch. So the key enabler for the chiplet is going to be, which is going to enable the communication, is going to be the interface. Mm. So you got two dies, and now they're going to have to talk to each other. The common interface, they need to be speak to the same language, and that interface is going to be, has to be low power. Target usually in the industry is it should be less than 1 picojoule to move a bit. High bandwidth means to move 1 terabit per millimeter in terms of the shoreline, I would say, bandwidth. The latency, probably less than 5 nanoseconds, and the data rate at least 10 gig and scalable. So right now we are at 4, 6, 10, 12, 16 gigabit per second, 24 gigabit per second, 32. Some IP provider at 40 and 65 gigabit per second. That's going to increase the bandwidth. So how you're going to partition the chiplet approach? Well, so if you take your logic, which is your core compute, you can basically partition those into 4 segments. For example, this is called the homogeneous partitioning. They're the same process node, and then this is how you partition it. However, the heterogeneous partitioning, as you can tell from the node, it needs to be a different process node, and it could come from different fabs. So if you had your old-fashioned monolithic die where you have the memory block, logic, DSP, RF, etc., you may partition it. The memory could come from different process node, from a different fab. The same for the logic. The DSP could be another node with somebody else, and the RF, you're going to source it. And then you're going to assemble and connect all of those. So the interface, one of the things that evolved way back then was the Intel AIB interface. This was the first standard for the die-to-die integration. And then along with that, we had the ODSA, which is the Open Domain Specific Architecture, which is now part of the Open Compute, or the so-called OCP. And what this organization does is that it's got a bunch of groups for them to discuss and collaborate on the chiplet approach. Now, if you look at the AIB interface, again, this is very high level. I'm just going to give you some heads up, but you're going to have to follow up on all of that. The AIB, which was the beginning or the initial interface, it then converted into what is called the UCIe, the Universal Chiplet Interconnect. But again, the concept is the same. You got multiple channels, probably up to 24, and then typically 24 channels, and within each channel you got the TX and the RX to transmit and receive. So if you look at the bump pattern, You will notice that you got a bump pitch of 55 micron and is in a staggered type configuration. And it would look something like this. This is the edge of the die, and these are the bump pattern. So you got probably a TX over here, you got an RX, IOs over here, on and on and on. And back then, if you looked at the bump pitch for the AIB, it used to be at 55 micron, and then the projection was go down to 10 micron bump pitch. Obviously, if you go to 10 micron bump pitch, it's going to you go more parallel, meaning to go wider is going to lower the picojoule per bit. It's going to lower the power from 1 to 0.2. And of course, it's going to increase the bandwidth, right? From 1K, I would say gigabit per second per millimeter, now to 4 and 8K. And the data rate also increased from 2 gig initial, later to 4 gig, and on and on and on. So, so that's the evolutions of the die-to-die interconnect, which is now migrated to the UCIe type interface. So now you have all of these dies with the interconnects, interface and everything on it, and now how you're going to integrate it. So if it's a standard die with a coarse pitch, we tend to use the monolithic or the what is called the multi-chip module or the system in a package. If it's a fine pitch, we call it the 2.5D 3D or the system in a package. It would look like something like this. So what are the packaging options we have? Well, again, it all depends on your, I would say, device, the pitch, the thermal, the electrical, the form factor, and all of that. And typically, you can get a fan out, fan in, flip chip, wire bond. This is the through pins. I'm sure you've seen this. These are very old style, limited IOs. And this is the most advanced 2.5D 3D type packages. So depends on the market application. These are the flavors. So in order to select the right type of package, we're going to have to look into the requirement. Well, I mean, first and foremost is going to be the cost. We're going to have to look at the IO, I would say, density, the form factor, the electrical or the so-called signal and power integrity requirement, the thermal stresses integrity, and the integration mechanism, how we're going to have to integrate those. Now, let's talk about the integration mechanism. For integration mechanism, we got a couple of options. This is what I call it. The first choices are the one with the substrate, meaning we can integrate these devices using the substrate or without the substrate. This is the emerging area. If we use the substrate to do the integration, again, it could be a flip chip BJ, like we talked about it. You got a die and the substrate. Could be an old-fashioned, I would say, wire bond. It could be a die embedded in the substrate, or it could be 2.5D with an interposer between the organic and the device, or it could be 3D stacking. All of these type of integration requires the substrate. Or it could be without the substrate, meaning it could be either fan in or fan out. What do I mean by the fan in? Meaning we can use the surface of the die to relocate the position of the bump on the die and to increase the bump pitch. Or we can actually embed the die in a mold and then use the surface area to kind of fan out to increase the bump pitch. This is what we call it, the fan out. We call it the fan in. So let's talk a bit more about this thing. fan out versus fan in versus a flip chip. Here's a good comparison that shows what do I mean by that. So um, here's a standard flip chip package. You got a die, you got a substrate, which is over molded, and you can see the form factor. You can do the same thing without the substrate, meaning the die is embedded in the mold, yet no substrate. We use a couple of RDL, which is manufactured on the surface of the mold and the die to increase the pitch. Or you can do the fan in. So if you look at the fan out versus the flip chip, meaning if we compare these two type packages, obviously you can tell that this fan out is going to give you better performance. Why? Because you don't have the you remove the electrical parasitics due to the substrate. You don't have the substrate here. You have a few RDL, which is going to eliminate all of those big vias, and it's going to lower the capacitance. It does perform better. It's going to be thinner because you don't have the substrate. It's going to lower the cost because now you eliminate the cost of the substrate and the assembly, all of that together. You just build it right on the top of the die, and you're good, and you're done. And in terms of the thermal, it's going to be much better because if you eliminate the substrate, which is acting as a barrier to heat to conduct through that, you can now have a better conduction through your board as well. Now, if you compare the fan out versus the fan in, you can tell that the fan out style can support higher I/O counts. In fan in, you're limited to the surface of the die only. And this is going to cover a wide range of application, right? It does basically the same job as the flip chip, but again, it's got its own limitation as well. I'll talk about it. It's going to be ideal for the system in the package and is thermally enhanced if you compare these two. So let's talk about the wafer versus the panel and the cost of the ownership. So to do the wafer level fan out, you're going to have to reconstitute the device on a surface of a 12-inch. Typically 12-inch, I would say wafer, right? So how many die you pack on the wafer is going to determine how many packages you get out of a 12-inch, I would say wafer. Of course, these areas are not being used, right? So the utilization ratio is less than 86%. So for a die size of 10 by 10, you get probably around 400 dies per wafer. Now, if you make this thing a square, make it a panel, 510 by 416 millimeter square panel, the utilization ratio is going to be better than, I would say, 90%, right? You can fit more into panel. Same die, on this size of panel, you can get 1600 dies. That means if you process this thing once, you get 1600 packages in one shot. So you say, well, what if I increase the panel size instead of 510? And what about if we use 600 by 600 millimeter package of the panel? Well, the utilization is high. Now you get about 2600 dies, 1,000 more packages. So simply by having a larger panel, you can go to a much higher volume production and lower the cost as well. So the fan-out technology options, this is important because, again, if we do the panel, if we do the wafer level fan-out, this type of fan-out packaging, it supports line width of 1 to 5 micron line with spacing, right? The dielectric is typical SiO2. For this type of line, we use the Damascene process and the advanced pick and place stepper. And the provider of this type of packaging is usually foundries as well as OSAT, and is used for the higher end type application. You can also use the same wafer if you need a line width of anywhere between 5 to 20 micron, which in this case you can use a PI for the dielectric instead of the Damascene process. You can use the plating process, PCB style type process, and this is going to be available at the OSAT and it's going to be at the middle end, or it could be the panel bump, the line width of 10 to 20 micron, using the polymer as a dielectric. And again, this could include the SMT pick and place equipment. You need the laser, the direct imaging is going to be available at the OSAT and the PCB, and it's going to be at the lower end, and it's for high volume. Okay. So how do we decide for the fan out panel level of the packaging? What are the driver for the PLP? One area is the computing, automotive, wearable, the mobile, RF SIP, memory, and the MEMS sensor. Again, the reason is that, I mean, the reason that you want to strive for the PLP is make it thinner, better thermal, better electrical, and is ideal for SIP. And the other thing, because this is panel, again, the cost, the utilization is high. And of course, almost 50% cost reduction compared to the wafer level. And then you get the higher package quantities. We already talked about that. Many companies invested in this area, PowerTech, back then, a few years ago, 1.63 billion in the construction of a PLP fab. TSMC spent 6.2 billion for the construction of new fab just to support this wafer level fan out. Semco, almost $500 million in the last 2 years on building the fab for his own product, like the Galaxy Watch and etc., based on the PLP. And if you look at the market trend, you can definitely tell that the wafer level fan out production, it used to be on a 6-inch back in 2010. The wafer size increased to 12-inch, and then the panel, to increase the throughput, the panel level packaging was introduced as of 8 to 10 years ago, and it started to increase, and now we are at the panel level packaging. We've got about 10 minutes. Let me talk about a bit about the choice for the substrate. Substrate is very important. So, we talked about it. It could be silicon, could be organic, or it could be glass. Any of these things. The organic, this is what is being used for many years, is already in production day in, day out. But these type of organic, it's got the scaling issues, challenges, meaning you're so limited to the trace width and spacing. For example, the vias that we use in this type of substrate is require a large capture pad, which is going to limit the connectivity in the vertical direction and is not suitable for the fine pitch interconnect. And the other things like the coplanarity, the warpage, all of those are the issues, challenges with organic package. But silicon interposer obviously is got you get very fine line within a spacing, but your concern is about the cost, right? The etch time, the insulating the vias, and the manufacturing aspect of it, and is limited to the wafer size. Now the glass, which is emerging, I'm sure you've seen it, right? About the Intel, announcing about the glass interposer or the glass substrate. Manufacturing the cost of manufacturing the true glass vias is got its own challenge. The thermal conductivity is very low compared to silicon. The glass is almost like an insulator. However, in terms of the electrical, it's got very good electrical. It's got a CTE match very close to the silicon, so the reliability is good. The electrical is good and is available in a large panel size. It's not like a silicon constraint to the wafer size. So now you got all of these things. The only thing is going to be the thermal conductivity and the via formation, which is now being streamlined. So all of these are being resolved. So it seems like the glass has got good prospect to replace all of these things. But at the same time, the silicon is a key player and is always there and is going to be there for many good reasons. So the organic substrate is good for the low cost mainstream type substrate, and it comes with various structures like the build up like a 10 to 10. So you got a core with the multi layers on the top and the bottom. The body size could be as big as 100 by 100 or 120 or 150 by 150 maybe. In terms of the trace center spacing, it could be 5 and then when I say 5 micron, it could be in a very small area within the die shadow area to be able to escape that, and all the way to 18, 25, 35, or etc. And this is suitable for a wide range of applications. Yet the silicon is a multifaceted substrate. It's got high aspect ratio TSV, the true silicon vias. You can go to large body size. It's got better coplanarity. The interposer can be a standard substrate by itself. It could be, it could give you the number of the layer that you need. You could have sub 1 micron line within spacing, meaning very wide bus we can manufacture and design on the silicon. It's got excellent thermal conductivity. Keep in mind that in IC packaging, that the thermal is the key, is really, really important. And that's one of the advantages of the silicon. We can do high-speed signaling. We can embed within the silicon. We could have, in fact, active interposer, meaning we have in some area of the interposer, we can have some transistors as well. We can also do the wafer level fan out. So, we talked about this thing. If you can have this silicon interposer, and with the chiplets could be the UCIe or the Intel AIB interface that is going to connect through the interposer, and this whole thing can be assembled on an organic substrate. So the silicon, there are a wide range of possibilities. You can go to a large body size, 50 by 50, 60 by 60, or on and on. And the question that you could possibly ask is that how can you achieve such a large, I would say, body size for the interposer? Keep in mind that we can always stitch the reticles together. So you can stitch 2 reticles with 100 nanometer across the shot. And then, of course, when you increase the interposer size, you want to make it thicker, right? So that's going to increase the aspect ratio. So now we can make through silicon via with 10-100 aspect ratio, 20-200, 25-300, etc. In terms of the RDL, we can have either both the damascene and the plating. For example, 4 more damascene layer with 0.5 macron line spacings, or we can have 4 more layers with the 5.5 polyimide type RDL. The true silicon via we can design, manufacture it as a coax, so that in terms of the electrical loss, we can mitigate the loss by making it like a coaxial type TSV. We can embed the passive inductor in that. Again, we can have active interposer and the fan out, and we can package the chiplets on that. There's a lot to talk about the manufacturing and all of that. I talked almost 55 minutes, and I want to give it, and I'm going to stop here, and I'm going to open up to question. I'm sure there might be some questions, so that I can, in a few minutes, I can answer some of the questions. So, anybody has any question, feel free to ask. Well, thank you for your attention. Any question?
Tribhuvan, ma'am.
Sir.
Yes.
Any other queries?
Participants, if you have any doubts, you can clarify it now.
Keep in mind that this was just an intro. I understand that there could be a lot of question coming up, I would say, later on. I hope I managed to get the key message across, at least to familiar everyone with the terminology. Thank you to everyone.
Thank you, sir.
Thank you.
Can we end up the session, ma'am? Okay.
Yes, sir. Thank you, sir. Thank you for your presentation.
Okay.
Hope it will be useful for all the participants. Everybody will learn certain things about packaging. We hope, sir. Thank you. Thank you for spending your precious time with us. Thank you.
It was my pleasure. Have a great event. Okay. I'll take
Thank
off.
you.
Thank you, sir.
Bye-bye. Bye.
Thanks, sir.
Bye.
Participants, kindly fill the feedback form posted in the chat box. And also, one kind request to the participants. Participants who are registered in the mail ID are requested to come to the Google Meet. I'm daily sending the meeting link to everyone. The link which was sent to me, you come to the meet. Tribhuvan, ma'am.
Sir.
Actually, ma'am, irukangala?
Irukang, sir. Irukang.
Okay. Ma'am.
Thank you all.
Thank you all. Can we stop the recording, ma'am?
Yes, sir.
Okay, ma'am.